today if DP flow measurement is expensive, complicated, and inaccurate, or in fact it is indispensable for many applications. Let's start. So what we will see today in the webinar is first I will start with the physical basics. I think it's important to understand the physical basics of differential pressure principle. A lot of you gentlemen will already be very experts on that anyway. For the other ones, I will do this in very brief. I want to show the principles and what is the advantage and disadvantage of this physical principle. After that, we will have a comparison with alternative measurement methods for different fluids. We will talk about classic primary elements, which is venturis, orifices. We will talk about the delta flow together with sys-MMF, which is a multivariable transmitter. And we talk about applications. And as I said before, we will have plenty of time for discussion afterwards, but feel free to write your questions while the presentation into the chat. And after the presentation, we will have plenty of time for discussions. Okay, let's go into the principle of the differential pressure measurement. The differential pressure measurement, basically, it's the law of Bernoulli, which is the constancy of energy. So the principle is very simple. So we have here a scheme of a Venturi type flow meter, and you have a control phase 1 and a control phase 2. And we have in a fluid, we have two types of energy which are relevant here. It's the kinetic energy, which is the energy of the velocity of the fluid. And we have the pressure of the fluid, which is the potential energy. So if you look here in the control phase 1, bigger diameter, your flow velocity is low, therefore the pressure is high. In the control phase 2, the velocity is higher, so the fluid needs to come through this bottleneck, therefore the pressure is lower. So if you understand that the energy is constant, then you can make two equations for the kinetic energy and the potential energy. And by this, you can, by intelligent removement in the formulas, you can calculate the mass flow in the end. So in position 2, speed is higher, so the pressure is lower. I think this is very well to understand. We have here the result of a simulation. So you see here a Venturi, and we have here the P1. Red color means high pressure, and here in the bottleneck you have a higher velocity, so the pressure is getting low, blue pressure. So that's what you can see in a simulation, and that's what we see if we do a measurement in a Venturi. So this is how a Venturi looks like physically. So this is a pretty big Venturi DN400. So you have the big control phase here. You have in this case a number of tappings, and they are connected with a ring pipe. And here you take the average dP in this control phase 1, and in the control phase 2 in the bottleneck or in the neck of the Venturi, you have also 3 tappings at the pipe wall to get the dP out. And in this ring pipe, it's collected, and between control phase 1 and between control phase 2, you do the differential pressure measurement, and this differential pressure is a measure of the velocity. So as you know, we are world market leader with differential pressure pitot tube. So therefore, I also want to show you how the DP principle with a pitot tube works. Basically, it's the same, just with the difference. We do not increase the speed, but at the front of a pitot tube, you have locally a pressure, a velocity which is going down to 0. Here in the front point, you have 0 velocity, and you have a speed up of the velocity on the side here, and therefore you have local differential pressure. So at the impact point, the speed is lower, so we have a high pressure here. And since we speed up at the side of the probe, the velocity, then you have a lower pressure on the back side, and you have two channels inside, and at the front side you have a number of tappings to get this pressure. So here's the simulation of the pressure. So you can see here at front you have a very high pressure, red color, and on the back side you have a very low pressure side. And this is how a pitot tube looks inside of a pipe. So you have this profile, this very special profile of SysTech in a pipe, and you have a number of tappings to collect an average pressure in the pipe. Just one word about this profile. This is a patented profile of SysTech, where we have a smooth impact and we have the speed up curves. The effect of this profile is that you have a very high linearity in the resistance factor of the probe. This resistance factor is a basic calibration constant, and the higher this is really a constant at the SysTech delta flow probe, and not a function of Reynolds, for example. So this is why we have this very special profile. Okay, now one of the claims for differential pressure measurement is that the measurement is complicated. Okay, here are the basic formulas for classical primary elements. This one and for pitot tubes, they look pretty much the same beside this first part of the equation. And yes, this looks complicated, and it might be a little bit complicated. So, but if you look to these equations, then you can say that this front part of the equation is almost a constant. It's not a constant, in fact, but it's almost a constant. So if you look to classical primary elements, this calibration constant C is a little bit a function of Reynolds, but not too much usually. And the expansion factor for expansive media, fluids, compressible fluids such as gases and steam, this might differ a little bit from 1. For liquids, it's 1. But let's assume this is nearly a constant. The same is true for pitot tubes. For pitot tubes, we have this resistance factor here at the front side, expansion factor, and the diameter, which is a little bit a function of temperature by the expansion of the pipe by temperature. But basically, it's almost a constant. So under the square root, you have the differential pressure, which is measured, and you have the density, which is unfortunately a function of pressure and temperature. So under the square root, you have basically differential pressure, temperature, and absolute pressure, which makes dP measurement a little bit more complicated than other measurements. So you also need a calculation unit, a process system, or a flow measurement computer to calculate this. So differential pressure measurement is complicated. Who tells you that has a point, that's true. But there is a way to make it a little bit less complicated. One possibility to make it less complicated is our SysMMF, which is a multivariable dP transmitter. The good thing is that this equation, this ISO 5167 equation, is included in this two-wire transmitter, which means this transmitter is not only measuring the dP, but also you can see it here in the display a little bit, the absolute pressure and the temperature. So you can put a PT100 on this, and then he will calculate the mass flow. So it's a multivariable transmitter, which can calculate, which can measure differential pressure, absolute pressure, and temperature. It calculates the mass flow in accordance with the standards. And the very good thing, which is special about the SysMMF, it only requires the setup of 4 parameters. Some of you guys might have some experience with multivariable transmitters. And as a matter of fact, most of our competitors, they are extremely complicated in setup, not for the SysMMF. So this is really very uncomplicated. And this is in the end the parameters which the SysMMF additionally needs. You can transmit them by HART protocol, or you can simply punch in these values by the front keys. Basically, you need to tell him what is the fluid, what is the maximum flow rate, And then you have to punch in a flow coefficient, which is calculated by our design software. So this is a numerical value, which includes all the calibration factors from the front part. And you need a K-EPS, which is a calculation compensation factor for the expansion factor. Very easy to punch it in. Setup can be done within a minute of this computers. And also a setup in the field is not a big issue. You don't need hard communication or digital communication. You simply go via the front keys and punch this in. So it's not that complicated anymore, differential pressure measurement. So this makes it much more uncomplicated. So the next point is differential measurement is expensive. So if you look, here is by simples a steam measurement. Then in addition to the primary element, in this example, it's a orifice plate. You need 1 to 3 transmitters. So you need one if you don't go for a pressure temperature compensation, which is mainly done for compressible fluids. But if you have an incompressible fluid, water or a liquid, you might only need a DP sensor. But if you're measuring gases or steam, usually you will need to add a temperature and a pressure sensor. And not only that, so if you look here to the scheme, you usually have a number of shut-off valves. So this is a typical application for a steam measurement. So you have shut-off valves at the orifice. You have a three-way manifold. You have degassing valves. The same is true for the pressure sensor. And for the temperature sensor, you also need a stud, a half-inch stud in the pipe. So a lot of pipe work is required, which is expensive. That's true. You need a calculation unit to calculate the flow from these 3 units. So you have expensive piping, expensive installation. So it's true, it's expensive. So this is a picture from Krone, how a very nice steam Venturi looks like. But you can imagine a Venturi like this. The Venturi itself is expensive. Also the installation of a Venturi. So this might be a 300 millimeter or something like that. You can imagine that this primary element is quite costly. And here you have all these condensation pots, the valves, the transmitters, the temperature sensor. Altogether, this is really an invest. So yes, it's true, it's expensive, but you already are expecting my answer on that. Delta flow together with a sys MMF for steam measurement is much more inexpensive. So you can install the delta flow just by one stud in the pipe, in your existing pipe. So no need for a spool piece or for cutting the pipe. You just drill a hole, 25 millimeter, install a flange stud, and with that you have all the measurements inside of the pipe. You have the primary element, you have a temperature sensor included, and you have the multivariable transmitter together with a three-way manifold, which can calculate the mass flow. So all is installed with just one flange stud. This is much more inexpensive. I would say there's a factor 1 to 3 or 1 to 5 compared with a Venturi installation that we showed in the picture before. So DP measurement can be expensive, but there's also very inexpensive solutions. Okay, the next claim for DP measurement is inaccurate. So how comes this argument, and is it right or is it not right? Number one, we have a squared measuring method. As I told you before, kinetic energy changes by the square with the potential energy. So the differential pressure, if you look to this graph, you have here flow on the x-axis and differential pressure on the y-axis. So if you are at 70% of the flow, you have 50% of the differential pressure, which is fine. If you have at 50% of the flow, you just have 25% of the differential pressure, which is fine. But if you are at 10% of the flow, you just have the square of 10% is 1%. You just have 1% of the differential pressure, which means In particular, at the low area, the resolution of the differential pressure is getting worse and worse. This is a physical truth. If you have big spans, let's say 1 to 20, then the differential pressure is just 1/400th. If you would square 20, then it's 400. So at 5% of the flow, you are just have 0.25% of the maximum dP. So small measuring range or high inaccuracy at low flow rates. The next point is you do not have only one sensor, but usually, at least for compressible fluids, you have 3 sensors, which are sources of error and which comes into the calculation of the accuracy. And beside the primary elements, so you have 3 sensors with an uncertainty, you have the primary element with an uncertainty, and the flow computer with an uncertainty. So in total, you have 5 physical sizes or 5 sensors which have their uncertainty and come in the total error calculation. So dP measurement is inaccurate. Let's see how far this is true. It is true by a certain amount. So because this is the physical and measurement truth of the measurement. But if you're looking today, there is also some good aspects. Nowadays, pressure sensors, dP sensors, and temperature sensors, they are very accurate. So 0.1% of the measured value is a standard. This is nowadays not an extra pricing or something like that. So even better accuracies. I think if you take a dP transmitter now from a high class manufacturer like Yokogawa, we are talking about accuracies of 0.04% or something like that. So highly accurate transmitters, which help for the total accuracy of the measurement. Primary elements have an uncertainty between 0.6 and 2%, but if you need it, they can be calibrated. So if you have primary elements, in particular delta flow pitot tubes or venturis or whatever, you can put them on a test bed and you can get the uncertainty of the primary element down to 0.25%. So if it's necessary, you can get a higher accuracy. But uncalibrated, they have typical inaccuracies between 0.6 and 2%, which is also not too bad. But anyway, if you need higher accuracy, it's possible. Once more, back to the multivariable. The advantage of a multivariable is that the calculation is part of the sensor. So no headache with digital analog and analog digital errors or something like that. If you take the MMF, all is together in one unit, and you have no headache with the AD and DA conversion. And another question which you have to ask yourself, if you have a process, if you have a measuring range of 1 to 10, for a lot of applications, this is sufficient. If you have 1 to 100, there's not too much processes which have that high measuring range. But then dP measurement might be wrong. But if you have 1 to 10 or even higher, we come on this with the next picture, then dP might be the right solution. So here I have 2 graphs. We have here the flow and the uncertainty of a compressed mass flow. So if you look to the total accuracy of value, then the blue one is a typical uncertainty of a 1% primary element. And here in a range 1 to 10, you are well under 1.5% of actual flow, which is not too bad. This is with standard transmitters, no calibration. And if you need a higher accuracy, and if you put the complete flow meter on the test bed, then 1 to 10, you are well below 0.5%, which is for compressible fluids an excellent accuracy. So there's not too much flow meters for compressible fluids, which are better than that. By the way, if 1 to 10 is not sufficient, there is a trick to get a higher accuracy. What we do from time to time is that we put a second dP transmitter, for example, at 20% of the flow, and then you get the accuracy line is going down here, and you can realize flow ranges up to 1 to 20, 1 to 30, or something like that, depending on the design of the flow measurement. But even if this range is not good enough, if this accuracy is not good enough, there is a possibility by splitting range to increase the low flow accuracy. Okay, that's about the basic physics and how the physics work together with the DP measurement. Now I want to tell you a little bit about alternative measurements. So there is lots and lots of alternative flow meters. I cannot cover all of them, but let's say I will go about a number of important alternatives. So if we're talking about gas flow meters, let's go with the first alternative, turbines, for example. Turbines are old technology, but they are very accurate. So turbines are still one of the most accurate flow meters. They are custody transfer flow meters, so expensive turbines. So if you have high-class turbines, they can be calibrated down to 0.25%, not of mass flow, but of volume flow. So if you want to have a mass flow, once more, you also will need pressure and temperature measurement, but very highly accurate flow meter. And they are widely used, still widely used in the hydrocarbon industries for natural gas, for example. If they are used in accordance to their specification, they have low drift and they have long recalibration intervals. So custody transfer recalibration intervals are up to 10 years. So very reliable, good flow meter. Anyway, there's also some drawbacks. Small temperature range, so you can use them for ambient conditions, but not for higher temperatures or something like that. They are very sensitive on dirt and condensate. So as you can imagine, you have a turning turbine wheel in there with an axis, and this axis is usually with no loop, or sometimes you even have a loop pump there, and you have to go there and pump some loop inside once a year or something like that. But these moving parts, they don't want to see particles and condensate. So this will lead to a drift and to problems with the accuracy. And another drawback is that these meters are quite expensive. So if you're talking about a DN100 high-class turbine, then we are talking about 10 to 15,000. If you are talking about 200 millimeter, it's a very heavy equipment. We are far away, far higher than 25,000 euros. There's some turbines which are less expensive, so-called quantometers. They might half of the price. They are in the range of 1%, but anyway, expensive flow meter. And if you need mass flow, you still need temperature and pressure compensation. So typically they are used on natural gas pipelines in the hydrocarbon industry. So another widely used technology in gas metering are thermal mass flow meters. They have also really pros. One is they really have a large measurement range. So if you want to see 1 to 50, 1 to 100 or something like that, this is possible with thermal mass flow meters. In particular, on the low end, they have an advantage. So they can measure very low flow ranges, and they have a very high accuracy on the low end. By the way, their physical principle is just the opposite of a DP measurement. So high resolution at the low flow rates, but low resolution at the high flow rates. So at high flow rates, the inaccuracy rather gets higher. Installation is easy, similar to pitot tube. So you just have a single stud where you install it in the pipe. And a big advantage is it's a direct mass flow measurement. So no temperature and pressure compensation. You directly have mass installation. Cheap, it's a question. So let's say the price range. If you're looking, for example, to thermal mass flow meters in the automotive industries, they use them often as reference meters for test beds. Then you are in the range of 15 to 20,000 euros. So not too cheap, but on the other side, once more, automotive industries, it's very likely that your car holds a thermal mass flow meter inside for the engine. And this thermal mass flow meters, if you purchase it at your car dealer, it might be 150 euro. Volkswagen purchases these sensors at Bosch for approximately 10 euros. So the cheapest thermal mass flow meters are automotive mass flow meters at 10 euros. The most expensive are thermal mass flow meters in automotive industries at the test bed, 20,000 euros. So in this span, so cheap or not cheap, it's depending on the application. But there is also a number of drawbacks. Thermal mass flow meters are really expensive to dirt and condensates. A lot of people are not aware about this fact. So a lot of people, for example, use them in pressurized air systems, and they say, okay, this is dried air and it's clean. It's not clean. And for example, in pressurized airs, you have oil residues from your oil-free compressor, but in fact they are not oil-free. And typically in compressed air systems, there might be a drift of 3 to 5% annually of these flow meters. So be careful with that. Once more, in the automotive industries, in test beds, they are very aware about this fact, and they recalibrate these sensors within 3 to 6 months. So if you look for reference flow meters in the automotive industries, they have very short recalibration intervals. Be careful with that. Next point, drawback. Usually they are single point measurements. So there are some special construction, but usually they are single point measurement, which means the single point is representative for your whole diameter. So be aware that if you have not a perfectly flow profile, that the accuracy is not too high, too good there. And as I said before, you have a long-term drift on these meters, even on clean fluids. So thermal mass flow meters, they are perfect for bottled gas. So if you have, there are also very small thermal mass flow meters for the pharma industries, for the chip industries or something like that. Perfect meter for these applications. But for industrial environment, be careful. And compared to at least to DP meters, they have a limited pressure and temperature area where they can be used. Okay, this was the comparison for gases. Let's look for steam. A very modern technology, which is nowadays often of interest for people, is ultrasonic clamp-on. It's very sexy because it's contact-free. This is for sure good. You don't have to cut the pipe. So no interruption of the process, which is very interesting. But there's also some drawbacks of this technology. You have a limited pressure and temperature range. So clamp-on ultrasonic needs a certain density. So for low pressure steam, they don't work. So they just work for high pressure steam. Unfortunately, with high pressure, the temperature is usually also going higher. So this is limited. So usually the transducers can be used, for example, up to 350 degrees Celsius. And you need minimum 10 bars. So the range of steam where you can use them is limited. There's just a number of manufacturers who currently are able to do this. By the way, Systec is also working on this technology. We don't have it right now, but perhaps in the future. Since there's just a limited number of manufacturers, it's an expensive technology. So don't believe that you're getting with lower costs than a DP measurement. The cost will be higher. Ultrasonic measurement is a speed measurement or volumetric measurement, but for steam, usually you are rather going for mass flow measurement. So you need a temperature and a pressure measurement. At least the pressure measurement needs to be invasive. So if you don't have a hole in the pipe for your pressure sensor, you also need to drill in the pipe. But usually in steam systems, somewhere you can get the pressure measurement. Temperature, with some inaccuracy, you can do a clamp-on temperature measurement too, but this is needed. Another technology which is widely used in steam are vortex or swirl flow meters, similar technology. The technology works with Karman swirl street. I don't know if this is a correct translation. So in the end, you have a body, and after the body, you have a shadow body, you have a frequency. And these meters, they are really industrial hard environment flow meters, which is good. So they are robust, which is an advantage. They have a large flow span. The manufacturers claim 1 to 30, which is usually not acceptable because the dp pressure loss is too high then. But typically in industries, which is good enough, they have 1 to 7, 1 to 15, 1 to 20 in this range. So drawbacks is they are sensitive on vibrations and pulsations. So the shadow frequency, so this Comanche street of vibration, is in the range of 50 hertz to 500 hertz. So in this area, which means this is close to pulsations and machine frequencies. So be careful. So the vortex flow meters need to be installed in a quiet environment with low vibrations. There's also some restrictions in pressure and temperature. There are high temperature vortex, which are getting them pretty expensive, but I think modern vortexes, they usually end the high temperature versions as 350 degrees Celsius. Not 100% sure. Probably there is a manufacturer going higher, but in this range is the limitation. And from the diameter, there is also some limitation. So I think the smallest will start at approximately DN25. So for industrial ones, and between 200 and 300 millimeters, that's basically the end of the story. Might be there is a manufacturer who can do some bigger or smaller sizes, but let's say this is the typical range for vortex flow meters. And as every time for flow meters where you have the body with the flow meter, for sure, the bigger the diameter, the higher the prices. So the price of a vortex flow meter, I would say it's similar to a Venturi measurement. So smaller diameters, it's affordable. Bigger diameters, it's getting more expensive. Okay, let's look for liquids. The alternative number one in industries for liquids, at least for conductive liquids, is magnetic flow meters, which is the technology that you really can use. They are precise for smaller diameters, pretty inexpensive. Precise means typical accuracy is 0.5%, let's say between 0.25 to 1%, so high accuracy. You have a large measurement range. They are uncomplicated, so you install them and forget them usually. You get them for all diameters, so I saw magnetic flow meters with diameters as large as 2 meters and I believe even higher. But anyway, some drawbacks. The higher the diameter, the higher the price, which is clear. You need a conductivity, which means hydrocarbons, no-go. Desalted water, depending on the rests salination of the water. Be careful with hot water. So if you have water, the electrodes might not corrode, but there might be a coating over the electrodes, which gives you some headache. Another alternative, by the way, we have also our own product line now at Systec, which is the Systec Coriolis flow meter. A Coriolis flow meter. Highest accuracy currently from the flow meters down to 0.05%, which is extraordinary high accuracy. By this high accuracy, you can cover extreme big flow range with that. So nice technology in terms of accuracy and flow range. And you have in the flow meter, by the physical principle, a mass flow, so a direct mass flow measurement, and a density measurement is also part of the measurement. So you can even do some analysis for processes. So for example, if you have a binary mixture of alcohol and water, then you can, by the density measurement, calculate the alcohol content, for example. So very interesting measurement. widely used in the hydrocarbon, in pharmacy, and in chemistry. Also some drawbacks for sure. This is also a system which is working with frequencies which are close to machine frequencies. So you need a good mounting position without shaking pipes or something like that to make sure that you don't get a misreading by process frequencies or pulsations. And they are pretty expensive depending on the diameters. In terms of expensive, as Xystec, we have a extremely well-priced and extremely accurate Coriolis now in our portfolio. And limited diameter range. So there is extraordinary big, I think DN200, DN300 are the biggest Coriolis you can buy now. But this is really an invest. So I would say the main diameters for Coriolis are small diameters. They are starting even at a few millimeters, and up to DN100 is a price range where they are affordable. If you exceed the 100 millimeters, then it's getting extremely expensive. Okay, this have been some competing technologies in comparison. So now let's look for classical primary elements. What do we understand of classical primary elements? I would say these are the primary elements which you can find in the standards. This is typical venturis, orifices, and nozzles, and wedge meters. They are standardized. There's one which is not standardized, but I count it as a classical primary element. It's the V-cone. So what are the specialties of them? So if you're looking to the accuracy of classical primary elements, then the highest accuracy you can have with an orifice. An orifice is a simple device and it's inexpensive, which is good. And it has the highest accuracy without calibration of this classical primary element. So the uncertainty, if you look at the standards of an orifice, is 0.6%. Which is not too bad without calibration. So the calibration factor, the C factor of the orifice, you can get it with an uncertainty of 0.6%. Not too bad. Anyway, you pay this accuracy with pressure drop. So with an orifice, you have the highest pressure losses. You can imagine this, that friction and vibration and noise created by an orifice is much higher than a venturi. Venturi, very smooth shape. By this, the pressure losses are much lower. Anyway, the accuracy of a venturi, unfortunately, is the worst without calibration once more. If you look into the standard, then it's between 1.5 and 2%. It's similar to a nozzle. A wedge meter is even a little bit worse. But these two flow meters, they are much more expensive. It's a big construction, as you can imagine. An orifice, it's just a sheet of metal where you make a correct hole. That's very easy to manufacture on the drilling machine. But this needs much more money. But you have a much lower pressure drop with venturis. The same is true for nozzles. A wedge meter is basically a flow meter for very rough conditions. So if you have slurries or liquids with sand inside or even stones, then you still can measure, but the particles can follow under the wedge in the pipe. So this is for very dirty applications. A V-cone, or I call it an inverse venturi. From my point of view, it's very simple to a venturi. First off, the shape, you have some effect of flow conditioning. So the venturi, as the V-cones, they claim to have shorter inlets, which is the truth. So this is very good. And by this shape, which is a better shape than an orifice, the pressure drops are not that high compared with orifices. So these are the two main claims of a V-cone. From my point of view, there is not too much advantages compared with a venturi. It's also a spool piece. It's pretty expensive. The inlet conditions are the same as for venturis, so 10 diameters after an elbow. So not too much advantages, and it's not standardized. So therefore, My recommendation, if you go for classical primary elements, rather go for Venturi. But there might be some other advantages which the manufacturers might tell you of V-cones. I would prefer, if I go for classical primary elements, always an orifice. If I go for high accuracy and if I don't care for the pressure drop, orifice. If I care for the pressure drop, Venturi. Okay, what is the advantages of classical primary elements? You can manufacture them for virtually all pressure and temperatures. So question of pressure and temperature is just a question of the wall thicknesses and the material you're using. So you can use them above 1000 centigrades. You can use them for several hundred bars in the pipe. So no other flow meter which can be used under such circumstances. You can produce them for all diameters. I saw Venturis with 6-7 meters diameter or orifices and nozzles and something like that. And you can also manufacture them down to millimeters or even sub-millimeter dimensions. So for all pipe diameters, you have a good accuracy. Starts uncalibrated at 0.6 with a nozzle, and the wedge meters have an accuracy of 3 meters uncalibrated. You can calibrate them down to higher accuracies, which is a good accuracy from my point of view. Differential pressure measurements are highly resistant against dirt and condensates, depending on the construction. So you need to do a construction, then you have a very high robustness. You can use them for steam, gases, and liquids. Now let's come to the not so good points. So you have a medium measuring range with no splitting range, 1 to 7, 1 to 12, something in this area. The cost depends on the diameter and the fluid. So small diameters, they are affordable. The bigger the diameter, the higher the cost. The installation is complex, as we saw before. You need shut-off valves, piping to the transmitters, and so on. And you have pressure losses depending on the type. High pressure losses for orifices, lower pressure losses for Venturis. So, and now let's go in comparison with the delta flow, in particular together with the multivariable. We have also a practically unlimited pressure and temperature range. We manufacture to all pressures and to all temperatures in your process. Not to all, but we made probes for 1200 degrees Celsius. We made probes for 600 bars in the offshore industry. So I would say this is an area which physically covers almost everything. We produce probes from 1 inch, so not from 2 inch, not from 2 millimeters. For 2 millimeters, we also do the DF8, which is a small orifice. But pitot tubes we do from 1 inch, 25 millimeters up to 50 meters, which is the biggest we built so far. If somebody comes with 70 meters, we will find a solution for that too, but this is the range we produced so far. We have a good accuracy, down to 0.5%. Standard accuracy of a probe uncalibrated is 1%. We are extremely robust against condensates and dirt. So the tappings here are big, so condensates can flow back into the pipe. And also dirt, if you're talking about gases up to 1,100 milligrams per cubic meter, we are fine. For higher dust content, this probe can be flushed out automatically. We produce it for gas, steams, and liquids. We have a good measurement range, 1 to 10, 1 to 15 with a probe. If you do splitting range, it could be even higher. The good thing is the costs are low. The cost for bigger diameters, they have a linear price rise because the sensor is just a finger which has a linear change of the pricing. So if you have a Venturi, then you have a volume which you need to build. So this is much lower, in particular for bigger diameters. This is very interesting. And the installation, as I said before, is very easy. One flange stud in the pipe, you have installed temperature, pressure, absolute pressure, and all the valves in one fitting with one stud in your existing pipes. Last but not least, low pressure losses. So time is passing. I will go a little bit faster now about the application. Here's a nice application in a cement plant after the rotation ovens. We have here 100,000 milligrams, so 100 to 150 grams dust, which is extraordinarily high, 900 degrees Celsius and 2.8 meter diameter. The probes are since many years in operation with no issue. These probes are made of Hastelloy because it's very corrosive, and we are using a air purging unit. So each 2 minutes there is a pressurized hit of the air purging unit blowing out the pipe here, the probe here. So for 100,000 milligrams dust, you need to purge it. Here's an application, a wet application, biogas in a wastewater plant. Biogas is 100% humid, dirty. So from time to time, there's foam in the bioreactor, and this foam comes to the probe. No issue with the delta flow. The big tappings and the capillary-free construction make sure that the condensate goes back. It's hazardous area, X-transmitter. These applications work very well with the delta flow. This is an interesting application because the gas company didn't find any alternative meter. So we have the delta flow after gas wellhead. We have 250 bars. We have particles, humidity, and things like this. It's toxic because of H2S and X, and the probe is working since many years without any maintenance and without any wear and tear. Refinery installation of a delta flow in 50 meters height. As you can imagine, the delta flow, 400 degrees Celsius, 100% humidity, no problem for the delta flow. But this is 4.5 meter diameter, which means that installation here with the delta flow is much easier than if you install, let's say, a Venturi or something like that. So basically, the probe is perhaps 40, 50 kilos. So we had a crane here, but you could also pull it out with a rope or something like that. So installation costs are very low, and the probe is doing the job without any issues. An interesting probe, a retractable probe, which is used for blast furnace gas in the steelworks. You know, this is carbon monoxide, 400 degrees Celsius. This probe is retractable because they have a very sticky environment there. And retractable here means the profile, this is the inside diameter here, can be pushed back into this neck of the probe, and then you can close the ball valve and get the probe outside. Since furnace gas is very toxic, they don't want to have open process for sure, and therefore we built this very big quick lock, which is not very often the case. Engine test benches in the automotive industries, we're doing this more and more and replacing thermal mass flow meters. This is for exhaust gas at an engine test bed. Engine test beds have a very high flow range. Sometimes they have small engines at idle. Sometimes they have big engines at full force, which means they have a flow range here between 20 kilos and 4,000 kilos. So we made a spool piece with 2 probes here, a big one for the big flow, a small one for the flow range, and 2 valves to automatically switch on and off the small and big flow range. Small flow range 20 to 300 kilo, big flow range 250 to 400 kilo. We calibrated this device on our test bed. Accuracy over the whole flow range, better 0.5%. Very nice application. Here's a high pressure steam application, our delta flow high pressure steam. This is calculated with the higher pressure equipment directive ratings. So 585 degrees Celsius, 169 bar. Interesting here, this was a replacement of the Venturi, and the annual cost savings are approximately 200,000 euro per year. This is quite a number, just by energy savings of the pressure drop. And the Venturi already have a low pressure loss, but the delta flow are even lower. So they are saving 200,000 euros a year here. Last example here is a DF8. A DF8, as I said before, is not a pitot tube anymore. It's a small orifice. We manufacture those for high pressure applications or for different applications. In this case, for hydrogen test bed at a fuel cell test bench, 400 bars, we need gold-plated transmitters here. And in this case, it was a 4 millimeter pipe, so very small dimensions. This is the Delta Flow 8. Okay, I'm ready with the presentation. If you like the presentation, just take your mobile phone and go on this QR code and give us a good rating for that. Thank you for your patience, and I'm ready for your questions now.